In this video, we're going to continue our discussion of Taylor and Maclaurin series. The question here is to evaluate the integral sin x divided by 2x dx as an infinite series. Find the first 5 non-zero terms of the Maclaurin series and also find the radius of convergence. Our strategy will be to start with the Maclaurin series of sin x and use it as a building block for developing the Maclaurin series for the integrand and then integrating term by term to find the Maclaurin series for the entire integral. All right, let's start with the Maclaurin series of sin x. So sin x is equal to x minus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial minus x to the 7 divided by 7 factorial and so on. It's easy to memorize the Maclaurin series of sin x because sin x is an odd function and that involves odd powers of x. Now, we need to develop the Maclaurin series of the integrand, which is sin x divided by 2x. So let's divide both sides by 2x. So we get sin x divided by 2x is equal to x divided by 2x minus x cubed divided by 3 factorial divided by 2x plus x to the 5 divided by 5 factorial divided by 2x minus x to the power of 7 divided by 7 factorial and divided by 2x and so on. Now let's simplify. So we have sin x divided by 2x. The x's cancel out. We get 1/2 minus, and this x cancels with the x cubed, giving us x squared numerator, so we get x squared divided by 3 factorial times 2 plus x to the 4th divided by 5 factorial times 2 minus x to the 6th divided by 7 factorial times 2 and so on. Now that we have developed the Maclaurin series of the integrand, sin x divided by 2x, let's integrate both sides to find the Maclaurin series for the integral. So we have integral sin x divided by 2x dx. This is going to be equal to, so we're going to integrate both sides. So we have integral of 1/2 minus x squared divided by 3 factorial times 2 plus x to the 4 divided by 5 factorial times 2 minus x to the 6 divided by 7 factorial times 2. And we integrate this expression with respect to x. So now we will carry out the integration. So whenever we integrate an expression like this, we always get a constant of integration coming out. So let's write that first. So that's c plus integral of 1/2 gives us 1/2 x because we're integrating a constant, and integral of a constant, c dx, gives us cx plus arbitrary constant of integration. Minus, now let's integrate the second term. We get minus x cubed divided by 3 times 3 factorial times 2. We're reversing the power rule. Now integrate the third term. Integral of x to the 4th gives us x to the 5 divided by 5, reversing the power rule. We get x to the power of 5 divided by 5 times 5 factorial times 2. And integrate the last term, minus x to the 6 divided by 7 factorial times 2. That gives us x to the power of 7 divided by 7 times 7 factorial times 2. Now, we were asked to find the first 5 terms of the Maclaurin series, including the constant c. So we have basically 5 terms, 1, 2, 3, 4, and 5. So this is the Maclaurin series representation of this integral. Integral of sin x divided by 2x dx. This is very useful because it is impossible to integrate a function such as this. There's no elementary antiderivative for this function. So we're able to find the integral in terms of a power series expansion. In this case, it's a Maclaurin series expansion. So there is the first 5 terms. So first 5 terms. of Maclaurin series. Maclaurin series. Now, we were also asked to find the radius of convergence. So for the radius of convergence, sine x has radius of convergence that r equals infinity. An interval of convergence minus infinity to infinity. That means sine x, the Maclaurin series for sine x converges for all values of x. Now, dividing sine x by x and integrating does not affect the radius of convergence. So the radius of convergence of the resulting series remains the same. R is equal to infinity and converges for all values of x from minus infinity to infinity. That would be the interval of convergence. Interval of convergence for this integral. All right, thanks.